Okay, beta plus decay. So in this also could be called positive beta decay, also could be called positron decay. You might see it in any one of those forms. It releases a positron. Yeah, that's right. So I should particle emission. We should add in beta minus decay. We should add the anti-electron neutrino. So for the positron decay, or yeah, it releases a positron.
What's the flat symbol?
Yeah.
Antiparticle.
Oh.
Yeah. And releases an electron neutrino. Not an anti-electron neutrino, just an electron neutrino.
So it's just going to be that R thing without the long line.
That's right.
Is it actually?
No, it just looks like one of those seagulls that you draw in elementary school.
Gamma.
What's the letter called for neutrino?
What is that? I have no idea.
We're gonna keep referring to it.
It might be gamma?
No gamma?
No, it's not. Sorry, it's a squiggly V. It's a weird V.
Seagull.
Squiggly.
Yeah,
Seagull.
it's, I don't know what that is.
Wikipedia probably like
Let's look. Hold on. Greek letter. Greek letter nu. Yeah, lovely.
That's new.
Neutrino means small neutral one.
Small neutral one. Yeah, it has no charge to it. Okay, that's why there's no charge out here.
Well, that's
Pen. Oh, there it is. All right. General equation. So in this case, we're having a neutron, a proton, which converts to a neutron. So we've got this element X, again, with Z and A. That's right. In this case, it's Z minus 1. Z minus 1, A. Plus
E.
just takes time.
I actually have the inflection wrong on that, on the, if we're being, like, super anal.
No.
I have the inflection wrong on these
It's very important.
neutrinos. It's like, oh, I don't want to do that.
Your eraser's not spot.
My erase. That's fine.
Instead of pressing undo, you press.
I know. I really mess things up now.
That's hard to draw.
You're really
kidding me. No more seagulls.
That's weird.
It's not a seagull.
I'm just looking.
Why doesn't it be seagull?
Well, it's easier when it's not seagulls. Oh God. Wait, so there's no like subscript E.
Subscript B? No.
All right. Subscript E. Yes, there is subscript E. Of course there is. Come on now, Dingerski.
Oh, sorry, today's Wednesday.
You wouldn't want to forget subscript E, or else it wouldn't be an electron neutrino. It would just be any old neutrino.
What's that
Unbelievable.
neutrino joke?
Oh, a neutrino walks into a bar and bartender says, "What can I get you?" Neutrino says nothing. I'm just passing through. Because neutrinos do not interact with matter very often, unless you put like huge bricks of matter in their way, like heavy water.
I told you I didn't get any water in a joke.
Heavy water. Water made from hydronium, or not hydronium, water made from deuterium.
Mine were two. He just had some issues.
We can't
His
completely
device
disagree
was
on
running
whatever
out of
deuterium
gas.
is.
A neutron
What
walks
did
into
you
the
say?
bar.
Hold on.
It's similar to between and a neutrino.
Oh, I don't have an example of
Constant penetrating the
positron decay. Let me look one up. Alright. Oops, I don't want that. I want this. Okay, so that was
11-6 carbon.
carbon, 11-6, and then that decays into boron,
511.
511, and then plus our
Electron.
anti-electron, plus our electron neutrino. Boom. Okay, two more. Next one's gamma decay. You guys remember what particle that emits?
Mm-hmm. A photon.
Good, just the light particle. And the photon symbol, not to be confused with the nu, is the gamma. Which is
Oh, I think you did that wrong.
yeah, you're right. I did it wrong gamma.
It's just like it's like an upside down.
Like that.
No,
Yes, it is.
Yeah, that's it.
That's it right
Oh.
there. The positive.
it's the capital
yeah?
down.
It's like an upside down
Yeah.
lambda.
Yeah, it is actually.
Sure.
All right, general equation. Nothing changes. It's nice. Okay, we don't have anything that's changed here. We've got Z and A becomes still X, Z and A, except it's at a non-excited state, and the textbook denotes it if it's an excited state. On the left-hand side, the textbook throws a little asterisk out here
Why?
to show that it's
It's
excited.
excited.
Woo! All right. Plus, it releases our good friend gamma, which is 0, 0.
Why do you put the lines in the middle of that? Make sure it's
Just
different.
to-
Oh,
not
to show the
zero.
start. Yeah.
Why
not a
did
two.
you put the sign with like two?
Yeah. Come on.
I am not a Greek
You're not very good with your
master.
notation.
I know. I'm sorry. The Greek is Greek to me.
Aha!
Yeah.
Yeah, I don't get it.
You're ski.
I don't get it.
They say it's
What?
Greek. If something doesn't make sense, say it's Greek.
Why?
It's all Greek to me. Get it? Ha ha ha.
So a specific example. Let's do uranium.
Say it's HL
People forget it.
This hamburger go to the chicken steak. Let's take the ground steak.
That's going on YouTube. Just telling you. Okay, uranium plus our gamma particle. That's the easiest one to remember out of all of these things.
Because nothing really happens
Because
here.
nothing changes.
Except for the asterisk and the gamma.
And we've got one more.
Electron carrier, whatever it's called.
Electron capture. And I have to Google an example of this one.
Oh, it's just uranium.
You're
So
right.
238. Oh, there's nothing to copy.
This is the option we're learning as a class?
This isn't an option, this is core.
No, this is core. Yeah.
Oh, quantum
We're not even there yet.
Examples.
Aluminum.
Okay.
Aluminium.
Aluminum 1326 plus electron.
No, we have.
Oh, we have to do the general one first. Yes, that's right. Okay. So the particle emission for electron capture is again just electron neutrino.
So does electron capture only happen with metal?
Yes, yes. Mostly for metal because think about it. We have to have free floating electrons, right? And the only place that we have free-floating electrons are in conductors. Word. Alright, so this is the general equation.
But does a radioactive conductor then change the magnetic field?
Say what?
If conductor?
Very rarely. This one doesn't happen very often.
Okay.
Would it change the magnetic field?
Yeah, if it were to become radioactive.
Hey. Dimitri Skleer is not here today. No.
Okay.
My blood pressure's down because of this. not that he's bad. No, he just keeps me on my toes.
My son.
And that's recorded. Yes. He's not a bad student, he just keeps me on my toes.
You know his, actually I shouldn't say this. His name on Skype is something. Oh,
Yep.
I didn't say it. I didn't say it.
What's that?
So what happens?
What happens when?
What happens if...
Oh yeah, you're talking about radioactive decay? Nothing. Nothing. It's such a small part of the... It would be such a small component of the actual metal itself. It wouldn't affect anything at all.
Okay.
Okay. So general equation, we've got X, Z, A plus an electron. So this is the only one that we have something on the left-hand side of the equation. So since electron's massless, it doesn't change the atomic number, or sorry, it doesn't change the atomic mass, but since we're annihilating a proton, it decreases the atomic number by 1.
Oh.
So we end up
So
with...
A minus.
Yeah, that's right. No, Z minus 1.
Minus 1. A stays there.
And A stays the same. And we emit our neutrino.
Wait, wouldn't A also be A minus 1 then?
No,
Because the mass would be different too.
no, because it's just absorbing an electron.
Oh, it's absorbed. Sorry, yeah.
That's right. Okay, so nothing's changing. The mass will change a little bit, but not very small amount.
But what? What was that again? Proton?
1326. Hold on.
How does the proton thing go down?
Give me 1 second. I just want to write this first one. Okay, because the electron gets absorbed by a proton, and the charges cancel out.
So
Okay, the
becomes
negative
neutron.
annihilates the positive charge. Okay, even smaller changes one of the quarks from up to down.
Oh.
All right, and that becomes Mg 1226. All right,
So which
let's
one
kill it.
Is the Mg? Is
Let's
that
end it here.
Radioactive?
See, Mg is
What's
less
the-
unstable. It might still be radioactive, but it's less unstable than the previous step, the aluminum 1326.
And the electron neutrino will just find some other
It just goes off into the universe, and it like literally will keep going through the universe
forever.
until it runs into something heavy enough, which,
Wait, what?
like I said, there's they won't neutrinos will keep going until usually it has to be a man-made thing to absorb them. Like in Sudbury, the SNO lab, the Sudbury Neutrino Observatory. It's specifically they had this. I saw it. I was lucky enough to go 2 years ago, and I went on this just awesome tour where they took me 2.5 kilometers underground into the mines.
What?
Okay, so first of all, these neutrinos have to pass through that much ground. Because if you did this in the, you can't do any of the experiments on the surface because the regular solar radiation interferes with the neutrinos. It would mess up with the experiment. So you have to go far enough underground so that all of the regular gamma particles are absorbed by the Earth, and then so you go. It's crazy. You're walking through mud, like just dark, dank, exactly what you think a mine looks like. You're walking through like first you go down this elevator 2 kilometers, and you're just ears popping crazy. It's like a 10-minute elevator ride, and then you have to walk half an hour through this mine, and you think, what the hell's? And then all of a sudden, it's just crazy. All of a sudden, it's like, oh, you're at the door of this high-tech, crazy-looking lab where everything's all smooth walls.
Like a movie.
You have to put on a clean. You have to shower. You have to put on a clean suit. Yeah, that's serious.
Shower?
You have to shower. The first thing you do is go into the change room. Like there's two entrances, like of course men and women, but there's no other entrance to the lab. First thing you have to do is shower, and you have to put on one of these Tyvek suits, like a clean suit. It looks like a hazmat suit almost. And then they can bring
And
you
how
on a
did you
tour.
get to do that?
How much did you have to pay for that?
Nothing. It was free. They were doing outreach to physics teachers, which was awesome. And I'm like, yep, yes please. Yeah, it was pretty awesome. And they have this huge. It's probably in diameter, probably about the size of from the front wall to this wall, like from the front of the school. And it's a huge sphere where they have just heavy water. So the heavy water made instead of with hydrogen, instead of H2O, it's deuterium 2O. So hydrogen with a neutron, proton and neutron instead of just proton, just makes the water more dense. And that huge sphere actually captures that finally neutrinos are able to run into something that will stop them.
What happened then? Like,
Why did they
And it triggers and it releases light particles, which then triggers photoreceptors on the outside of the sphere, and they can actually detect the
So then
neutrinos.
every time it like hits it, it would go like it'll light somewhere.
It's individual photons. Like these things are so
Oh, you
super
can't see it?
sensitive.
That'd be awesome.
You wouldn't see anything. It would just
Yeah, that's what I thought it would.
no, nothing that cool.
Yeah, I thought it would be like a little like.
Yeah, that's right.
You know there's one guy in the
Probably
like exhibition that
Yeah.
you know radioactive.
You
They
can't
used
even like
to-
leave.
they didn't get energy from it, but it was pretty amazing.
It exist.